Okay, so let's start actually, although the number of students has dwindled quite a bit. Um, so actually, the next three lectures are going to be on a slightly different topic. Okay, just like in reinforcement learning, the most important thing, or uh, in reinforcement learning and online learning, the most important thing was it was not just about learning, but also you were worried about your decisions. Okay, that's why you cared about regret or how well you decide, and therefore you wanted to explore and exploit. And that's what we saw for the past three lectures. Okay, so that notion of trading off exploration exploitation was not there before so far in supervised learning and unsupervised learning that you've seen before. So that's why those three lectures were kind of a big delta. Okay, and of course, last two lectures about reinforcement learning, there's also this notion of value function, policies, and the notion of mark addition process, and many other things. So that's a those are all new concepts. So similarly, for the next three lectures, there's going to be a delta. Okay, and so the delta is not going to be in terms of engineering. So it's not about. So in fact, the next three lectures are not about deep learning, but they are about a unified way to think about any prediction problem or a unsupervised learning problem. Okay, and we'll in fact uh, this set of three lectures, I mean, these are just about what are called graphical models. And so most of the models that you've seen in the past, for example, all the way from linear regression models, ridge regression, logistic regression. uh, in fact, in the text processing lecture, we were talking about latent dirichlet allocation. So all these guys are special cases of graphical models. And there was a question about hidden Markov models at some point. That's also a graphical model, and we'll go through those examples. Okay. So the big delta for the next three lectures is going to be thinking in terms of random variables, their relationships, and how can you encode some sort of domain knowledge in a prediction problem or a supervised learning problem, unsupervised learning problem. Okay, so it's all about encoding domain knowledge. There in deep learning, it was not really clear how to encode domain knowledge. Of course, CNNs were encoding some domain knowledge about the image properties. Okay, but here it's going to be more general, and we'll see what are the type of domain knowledge that can be incorporated. And so I'll discuss some details about how the next three lectures are gonna progress. But for today, what's the goal? First thing, what is a graphical model? Okay, and the short answer is just a joint distribution with a graph associated with it. Okay, it's like saying, oh, I know a joint distribution with a bunch of variables, and here's a graph which also kind of captures those random variables as nodes. Okay, so that's a graphical model. And second thing is how to, of course, relate. There's a graph, there's a joint distribution. How do I relate the graph to the joint distribution? And the graph is going to tell you something about what are called conditional independence assumptions being made. Okay, so this is what I mean by domain knowledge. For example, we'll see a network later on, maybe in the first hour, where there are some variables like intelligence and difficulty level of an exam, but what you observe is things like grade or SAT scores. Okay, so there could be some questions like, oh, is grade and SAT score independent given if I can measure intelligence? Okay, things like that. So graphs are going to encode such conditional independence properties. The third goal for today is going to be third and fourth goal are going to be about different types of graphs. So basically, there are two types of, I guess, there are many types of graphs, but two broad classification in this category is going to be directed graphs and undirected graphs. Okay, directed graphs just mean that edges have directions. So an edge from node 1 to node 2, if there's a direction to it, that it is from 1 to 2, it's going to be different from an edge which doesn't encode direction. Okay, so we'll see what's the difference between, not so much what's the difference between those two models. Okay, though they are basically two ways to represent these types of domain knowledge, which are basically conditional independence information. Both have their uses, and so we'll look at one after the other. Okay, look at them one after the other. So that's the agenda for today. So what's a graphical model? What's a graph and what's its relation to distribution? And some details about directed graphs, graphical models, and some details about undirected graphical models. So actually, directed graphical models are also called Bayesian networks. So some people who have heard of this term, Bayesian networks, that's what these are. Okay. And we'll also try to, remind me if I don't discuss it, there's something called a Monty Hall problem. Some of you might have heard of it. We'll discuss how to think about the Monty Hall problem maybe during the before the break or after the break. Okay. Um, okay. So today's outline, motivation is where I'll talk about what are these three parts that we're going to look at today, next lecture, and the next lecture. Okay, because the biggest delta is going to be you learn deep learning, and deep learning was not a big delta because you've already seen so much of supervised learning before. Okay, in previous courses. But what you have not seen was the trade-off exploration exploitation. That was the three lectures before, and now you'll see a different way of looking at supervised and unsupervised learning problems. Okay, where the different way is going to be more about emphasizing certain type of domain knowledge. Okay, some metadata. Okay, and the metadata is not going to be additional features. Okay, it's going to be actually some sort of relationship between columns of a table, for example. Okay, so we're going to discuss what this next three, today, tomorrow, next lecture are gonna be about. Then we're gonna start briefly review what graphs are because everybody needs to be on the same page. What's a graph? What's a node? What's an edge? Things like that. And then we're going to talk about directed variations and undirected variations. Okay, that's the agenda. So why is graphical models important? There was this, this is just a snapshot from, I think, Julia Pearl is a very prominent researcher in this area, and he got what is called the Turing Award. It's the topmost award for researchers in computer science, and computer science is eating the world, kind of. So it's a kind of a big award, just like the Nobel Prizes. Okay, and so his work on graphical models and causal inference was recognized, just 8 years ago. So it's basically an important domain. Okay, and in fact, there's been a resurgence on this topic of causal inference, where graphical models are, at least if you know graphical models, you can kind of at least work on some parts of causal inference easily. Okay, causal inference is all about finding a cause-effect relationship between variables. Okay, like smoking causes cancer and things like that. That requires more machinery than what we're going to look at in the next three lectures. But if you know this, then that will be kind of easy. Okay, so. Um, so this is a little bit older slide. So we've seen unstructured data so far. Okay, so we've seen basically deep learning methods, structure. I mean problems on vision, text, and audio, and we've also seen control. Okay, so control was the decision making. The policy was in a state taking an action, and the action was not just a label. It was basically some complicated action, for example. And so what we're going to switch now. So this was about decisions. This was about usual unstructured supervised learning, first bullet point. But now what we're going to do is go back to non-decision making settings, as in like, let's not worry about the complex decisions that are happening, for example, in this case. But now let's look at structured data, but in a way where we can encode domain knowledge. Okay, and there are some successful examples. Let me just give you the examples here. There's something called Kalman filtering. Okay, it's a really old technique from 1960s, and it's basically Kalman filtering. Is essentially like an equivalent of like a time series model. Okay, time series model of the world, and so but you will see that this technique is essentially like can be you if you know graphical models, this technique will be very very obvious to you of in its problem wherever it's applicable, like a time series setting. Graphical model language can make you understand this really well. There's also something called decoding. Okay, so analog signals come to your cell phone, they need to get decoded into actual real signals. The decoding also can be done using the notion of graphical models. Okay? And the last thing is hidden Markov models. They are also related to Kalman filtering, but again about some sort of time series model where some things are not observed, some things are observed. Okay, so we'll actually look at what hidden Markov model is pretty soon, so it'll be more concrete. But these are some successful examples of very different tools and techniques in very different domains, but they can all be kind of very easily discussed if you kind of understand the underpinnings of graphical models. Okay. But a very, very rough contrast between graphical models and neural networks is that neural networks are typically deterministic, although you have now Bayesian variations of, or basically, I would say, neural networks which also encode uncertainties. Like they don't just predict, oh, this is the probability with which this is a cat, but also there's a probability, but the probability is between 0.3 and zero point 0.6 as a cat. Okay, that's like some sort of uncertainty estimate. So, but typically deep neural networks have been more deterministic in nature. They're just functions which map from some input to some output. Whereas graphical models are inherently probabilistic. Okay, they are basically trying to relate random variables. Okay, and we'll see what those random variables are. They'll have names. They'll have specific meaning. These random variables, and most of the emphasis is about relationships between these random variables. Like I was talking about intelligence, grades, SAT score, difficulty level of the exam. Those are all related. These are all going to be random variables, and the emphasis is going to be how are these random variables related. Okay, so that we can do inference, we can do prediction, we can predict somebody's grade given the difficulty level of the course and their SAT score, for example, things like that. Okay, naturally these types of models have relatively low capacity in the sense of think of linear regression, right? Linear regression is actually an example of a graphical model. Okay, but that linear regression is not going to beat a deep neural network, because deep neural networks can capture all sorts of patterns, right? So that's what this third point just means, that there's less emphasis on like capturing very complicated patterns, but more emphasis on giving meanings to random variables and how understanding how they're related to each other. Okay, and that's what ties to the last point, that domain knowledge is easy to encode, and there's certain type of domain knowledge. So I'll tell you what the type of domain knowledge is. Okay, and domain knowledge is typically hard to encode, and that's why you see all sorts of new network architectures, all the sequence to sequence models and things like that. They're trying to capture some aspect of the domain. Okay, so let's understand how we're going to proceed in the next three lectures. The first lecture, today's lecture, is all about representation. Okay, so we're gonna understand these random variables, their joint distribution, and how it captures uncertainty between these random variables. Okay, and second thing is how are you gonna capture conditional independence properties? Okay, maybe some random variable, maybe what is it called? Intelligence has nothing to do with difficulty, but you have to capture it in some way. So how do you capture it? Okay, there has to be some like a probability of difficulty and condition, and intelligence have not, should factorize into probability of difficulty times probability of condition, probability of intelligence, right? So things like that, and then we'll visualize this metadata. When I say metadata, I'm only talking about conditional independences. Okay, so this is the type of domain knowledge I mean. When there are different types of people say, when the people say domain knowledge, they mean a lot of different things. Sometimes these are literally attributes. So like some domain knowledge can be, oh, this data was from city of Chicago and that data is from city of New York. That's not what I mean by domain knowledge. For us, domain knowledge is going to be relationships between random variables. Okay, in particular, we care about independence relationships between random variables. Subsequently, so once we understand representation in today's lecture, we'll talk about how that representation is going to help a couple of things. Okay, first thing is inference. Okay, inference is this general problem of given data, learn something. Okay, so learning parameters is also considered a inference problem, but inference is all about finding conditional probabilities, okay, or marginal probabilities. That's the name. So when people say I want to infer, okay, it's all about finding. When they want to do inference, it's all about there's going to be some random variable and they want to compute some conditional probability of that random variable taking some value given some evidence, okay, or given some data. Okay, that's what people mean when they use inference. Inference is a specific term here. Okay, and the third part is going to be learning. Okay, learning these joint distributions. Okay, so for us, the primary object is always going to be a joint distribution. Just like in supervised learning, there was a joint distribution between input and output, right? X and Y. Or even in unsupervised learning, there was a distribution on x's, like in clustering and so on, or Gaussian mixture models. So learning is all about finding the parameters using training data. Okay, so this problem we've already seen some variations of how to solve this problem. Okay, for example, some of you might have seen maximum likelihood estimation. If you have taken my course, I talk about maximum likelihood estimation. That is an example. That's an example, I guess, technique in this third bucket. Okay. The second bucket, inference, is all about computing a marginal distribution or computing conditional distribution. And this we know what is the conditional distribution, probability of A given B, and you know what's the formula for it, right? For example, a simple formula. But that's not enough. As you have more and more random variables, it's not easy to compute these guys. So we'll learn how to do that computation. Okay. So let me skip this picture. Okay, so let's talk about, let's slowly introduce ourselves to this notion of a graph and a graphical model. And the first example is this thing called hidden Markov model. Okay, so what is a hidden Markov model? Okay, it's when people, whenever we say we have a model or instance here, it's going to be a bunch of random variables, and in this case, there's going to be 12 random variables, y1 to y6 and x1 to x6. Don't worry about that particular graph, okay, which relates those random variables, but we have 12 random variables. Okay, it's called a hidden Markov model because there's going to be some Markovian property. I'll get to the Markovian property, but let me say what hidden just means. Hidden means that some of these variables are not observed. Okay, what are those variables which are not observed? Convention is to shade the variables which are observed. And in this case, x1 to x6 are observed, and y1 to y6 are not observed. Okay, so it's like an example could be like y1 to y6 is your state, your internal state, how enthusiastic you are, and maybe x1 to x6 are how did you do on a quiz. Okay, so 6 quizzes. You are enthusiastic, so you did well, but your enthusiasm level in the previous day or the previous week influences how much enthusiastic you are the next day. Okay, and so there is this hidden Markovian structure on enthusiasm levels, and for given enthusiasm level, you can do well or not well in the quiz. Okay, but we only observe the quiz score. We don't observe these hidden enthusiasm levels. Okay, so that's the an example of a hidden Markov structure, and it's used. So what's its claim to fame? It was used in speech recognition quite a bit till till 2010s. Now actually you'll see deep learning, and we have seen deep learning based architectures for speech recognition, at least examples of it. But it has uses in many other settings. Okay. Actually, it's a very useful technique or model to use whenever you have time series data, because it's literally relates. You can think of these indices as time. Okay? So you can literally have a time series model which has some hidden random variables, but you observe something else, like sensor readings. Sensor readings would be noisy versions of the actual state of the system. For example, car situation, whether it's good or bad, things like that. Okay. So what is the Markov structure? It just says that this joint distribution between y and x, okay, is boldface y, boldface x. Just means that this is y1, y2, y3, y6, comma x1, x2, x3, x6. Okay, all those 12 random variables, they factorize in this way. Okay, so this joint distribution between these 12 random variables is split into uh, these terms where you start with the left hand side leftmost random variable y1. Okay, so there's some probability of y1, and then you have a probability of x1 given y1, x1 given y1, and then you also have a probability of y2 given y1, that is this, like y2 given y1. Then you have x2 given y2, that's this, x2 given y2. So for every y, there's going to be xi given yi. So x1 given y1, x2 given y2, x3 given y3. So many such guys. Okay, 6 of them actually, and probably y1 itself. And then there will be 5 other terms, which will be y2 given y1, y3 given y2, y4 given y3, and so on. So this is the Markovian structure. Okay, it's just saying that the value that this random variable yt takes, given the previous random variable, doesn't depend on what are the two time steps ago what random variable there was. Okay, so that's the Markovian structure. This is the Markovian structure. Okay, or memoryless structure. Given the immediate preceding random variable like y4, y5 doesn't depend on any of these three guys. That's what this is encoding. Okay. So we'll kind of go into details of how do you write this in general for a generic graphical model, but this is an example of a graphical model. So here, these are random variables, but I'm representing them as nodes. Okay, this is like a graph where there's some edges, in fact, directed edges. Okay, this is going to be a directed graphical model. Okay, and if I know this graphical model, there's going to be some generic techniques to do a computation, which is what I remember. I said there's going to be some techniques for inference. There's going to be some techniques for learning. Okay, although this is a specific directed graphical model and there's some specific algorithms for learning, doing inference and learning, if I know the general technique, I can always apply this to any specific model. Okay, in this case, this model. Okay. So, so any questions about this? I mean, don't worry about these statements, but any questions about this joint distribution? Okay. So, so this bullet point is what is the Markovian structure? It's called the transition probability between two random variables. Okay, and xt given yt is called the emission probability. It just means that what I observe just depends on what is hidden and nothing else. Okay. And there's a lot of conditional independence properties. As I said, given y2, y1 doesn't depend on anything else. Okay. Given y2, y1 doesn't depend on other guys is an example of conditional independence property. But we'll kind of derive the reading such conditional independence properties mechanically is what we'll get to today. Okay. So don't worry if you don't know why this is true for this graph. Don't worry about it. We will get there. Okay. So let me specialize this to a situation where I can talk about. So in this slide, what the goal is to say what are the parameters of this model. Okay, I showed you a graph. I showed you a joint distribution. You can ask, oh, what are the parameters of this distribution? So there has to be parameters, right? Some numbers which encode this joint distribution. Like, okay, if y1, y2, y6 take some value, x takes some, x1 to x6 take some value. What's the value? What's the probability of them taking these values, right? You can compute that if you know these guys, right? So here is an example where we'll simplify the problem. It's called a homogeneous hidden Markov model, where the conditional probability of yt given yt minus 1 doesn't depend on t. Okay? Doesn't depend on time. In a sense, and also the conditional probability of xt given yt, whatever the numbers need to be encoded in that conditional probability, they don't depend on time. Okay, so that's a homogeneous hidden Markov model. In the sense that think of two parameters, beta and alpha. So let's say alpha is about this emission probability and beta is about this transition probability. Then you can say, okay, probability of x1 given y1 is some, take the alpha function, plug in x1, y1, I'll get some probability. If I plug in x2, y2, I'll get some probability. That's here. But I'll use the same alpha function. As in the same, alpha will have a bunch of parameters, right? If it's a function. Similarly, the transition probability is a function of two arguments, so it's fixed bunch of numbers, and given plug in these two numbers to figure out what number needs to go there. Okay, so actually let me write it a little bit more cleanly. So this alpha and beta, just think of beta as actually a matrix. Okay, it's let's say y takes three values. Okay, so and let's say alpha of 3 cross 5. Okay, so so what are these 3 and 5? So let's focus on beta. So beta is supposed to tell me two things, right? So it's supposed to tell me beta of yt given yt minus 1. Okay, given or whatever, it's two arguments. Okay, given those two numbers, you just look at, oh, y is, let's say it takes only 3 values, yt takes 3 values, yt minus 1 takes 3 values. You just look at, oh, yt is this, yt minus 1 is this. Maybe this is the yt was 2 and maybe yt minus 1 was 2. Then take this value, take this number. That's what this means. Okay, this term in that joint distribution. Now, whether it's yt minus 1 or yt plus 1 yt or some other two in time indices, doesn't matter. You always go back to this table and pick up the number, which means that you only need about 9 numbers to represent this joint distribution. Whether it's a 20 length hidden Markov model or like a 6 length hidden Markov model. Okay. Similarly, alpha is just saying for a given yt, so yt can take 3 values, xt can maybe take 5 values. Then it's just saying, oh, for a yt is equal to 2, xt took maybe the 4th value, then pick up that number. So all I'm saying is these are the parameters. Okay, so these 9 numbers here and these 15 numbers here. Okay, so 15 plus 9 are the number of parameters needed. There's actually some more parameters needed because you also need to know what is the probability of y1 itself. So if y is taking 3 values, there's another 3 numbers here. Okay, and everything else is pretty much determined by alpha, beta, alpha. So that those are 15 numbers. Okay, is that clear? 15 plus 9. Sorry.
What are some applications of homogeneous sugar?
So homogeneous hidden Markov models are basically where things are stationary. Okay, so in the sense that probability of do you know what a stationary distribution is? Like basically, think of a sequence of random variables in a time series situation. Uh, like every day I'm flipping a coin. Okay, so you have a sequence of random variables. They're also independent. Okay, it's not going to be a stationary sequence if the probability, the joint distribution between the first 10 coin flips landing, let's say heads. Okay, I want to know what is the probability that the first 10 coin flips landed head. If that probability is not the same as what's the probability of next 10 random variables landed heads, then it's not stationary. Okay, in the sense the parameters changed. Here, homogeneous just means the parameters did not change. Okay,
Okay.
that's all. So it's like stationary environments. It's not. Let's say you build a prediction model. As long as the test data is similar to the training data, then your predictions will work, right? Otherwise, if your test data is come from a different distribution than your training data, you know that your prediction will not work.
So for part of speech tagging, would you use this because there's only so many different parts of speech? Or
Oh, parts of speech tagging is basically about these parts of speech are what are not observed, but you observe the speech itself, like the words. So, but given the words, you can infer what's the most likely values that these hidden variables can take. Okay.
Oh, okay.
So, part of speech tagging is basically saying, oh, you observed the sentence. I know the joint distribution between the sentence and the parts of speech. Okay. Now, given the sentence, can you tell me what's the probability of y? Okay. And then you take the most likely parts of speech assignment there. Okay. So that problem is an inference problem. We are not solving that inference problem here, but that problem is like saying probability of y given x. If I already tell you alpha, betas, and stuff like that, then you can compute what's the probability of y given a particular sentence. Okay. But we'll get there for those who did not follow. Um, Here's a more simpler example. I started with hidden Markov model just to show you a more interesting graph. So this example everybody knows because Naive-Bayes model. Okay, so Naive-Bayes model again can be represented as a graph. So why am I showing this graph is because everything that you've seen, many of the linear models, logical regression, Naive-Bayes, they are all graphical models. Okay, so here is a graph. It's basically y and y as an output and a bunch of inputs. Okay, in this case, we are just asking. We only our vocabulary is of length n. Okay, we only can see observe n words, and let's say each random variable here is just whether a word is present or not in the current email, for example, and depending on that, you can say whether it's a spam or not. Okay. So what is the model? The model is saying, oh, there's going to be a random variable which is spam or not. Okay, like two binary valued random variable, and there's going to be binary valued random variables which are w1 to wn, which is the presence or absence of a word. Okay, this random variable is going to be related to each of these random variables in this way, in a directed way. Okay, there's going to be an arrow from this random variable to this random variable. Okay, that's a graph. That's given that graph. So that graph kind of represents what we think of in terms of Naive-Bayes. Okay, in the Naive-Bayes, we assume that given the y, these random variables, the w random variables, are independent of each other, conditionally independent of each other. Okay? So without this graph, if somebody asks you what's the Naive-Bayes model, what's the assumption, you will say, oh, in the Naive-Bayes model, I know that condition on the output class, okay, taking some value, the probability of all these features is actually decomposes as the probability of each individual feature. Okay, that's what this is. Okay? The product distribution. Okay, so this is what you would directly jump to, but this that we jump to that actually encoded using this graph because it's basically saying given this node, if I tell you what the value of this node is, this random variable has nothing to do with this random variable. That's what we mean here. So if I don't tell you this node, all these random variables are related to each other. Okay, if I don't tell you this, if you remove this conditioning, the random variables are related to each other because there's like arrows between them. Okay, but if I tell you this random variable, so this is like given, as in I have observed, then you can drop all the edges connecting to the observed guy, and then you have separated nodes, and therefore you can say they're independent. Okay, so we are actually going to formalize this pretty soon, but I wanted to show you that Naive-Bayes model corresponds to a graph like this, very simple graph, output, n inputs, and it's literally this graph is supposed to encode this conditional independence property. Okay, This property you should have seen before. How many of you have not seen this? Naive-Bayes property, that is just that given the class, the probability of a feature 1 has nothing to do with probability of feature 2, probability of feature 3, and that's why you have this product distribution of features. Okay. And so the picture on the right is actually what is called a plate notation, a simpler notation to represent this, because I don't want to repeat this n times. I just draw one edge and a box around it saying this thing goes from for loop from I is equal to 1 to n. It's just a compact way to show this graph. Okay, and we have actually seen this plate notation in LDA, which I think comes next one slide from now. Actually, next slide. So Naive-Bayes is a clear that's the graph, that's the condition, that's the assumption. Okay, this is not a joint distribution between all the variables. This is just showing the Naive-Bayes assumption here. Okay. Now let's focus on just this picture. Okay, ignore everything else. Forget this picture. Forget these text. Okay, let's just focus on the picture on the right side, because this is going to be a recap about latent digital allocation, a topic model from 2002 2003, which is kind of a workhorse. You don't have to know deep learning. You can kind of apply this to in an unstructured setting, basically like 10K filings or things like that. Okay, reviews or art newspaper articles and stuff like that. So what's the model? This model is, again, will have a bunch of random variables. In fact, the random variables are going to be everything inside these boxes. This is a random variable, theta d. ZID is a random variable. WID is a random variable. Okay. So there's this. So there's capital D of them. Let's say I have 10 documents. Then there's going to be 10 such random variables. Okay. And if each document has maybe 100 words, then there's going to be 100 random variables per document, which are going to be topic random variables, and there's going to be 100 random variables, which are going to be the word random variables. Okay. And so what is the model here for LDA? It's basically saying, oh, so this alpha and beta are parameters. Okay. Alpha is like a hyperparameter, which is gonna, it's like a parameter for a Dirichlet distribution. So what? So I'm gonna tell you the model here. So let's say alpha and beta are fixed. Okay, they're not random variables. So given alpha, first I'm gonna draw a sample from a Dirichlet distribution. You need to remember, if you get a sample from a Dirichlet distribution, it's gonna be a probability mass function. Okay, in a sense. If you're in 3 dimensions, you're going to get a sample from the simplex. Okay, a simplex is like a triangular thing. So this you must have seen before. Okay, this is 1 0 0 0 1 0 and 0 0 1. Okay, so this region here, the shaded region, is like a plane segment of a plane, and the digital distribution is just a distribution over points in this plane segment. Okay, to draw a sample, you'll get a three-dimensional number here, three-dimensional vector here. Those 3 numbers will sum to 1. Okay, this is on a positive ortho, so they're all positive numbers and they sum to 1. That's why it's a probability mass function. Now, Dirichlet LDA model is just saying that, oh, you've already given me alpha is some parameter of the Dirichlet distribution, from which I'm drawing for a document. There are many documents, like 10 documents. For each document, I'm going to sample this PMF. This PMF is going to be, let's say, 0.3, 0.3, 0.4. Okay, sums to 1, right? So if it's going to be a 3-dimensional PMF, we are going to be implicitly making an assumption that there are only 3 topics. Okay, so let's say we got this 0.3, 0.3, 0.4. Okay, one specific theta. Then what we're going to do is we now know the topic composition of that document. It's 0.3, 0.3, 0.4, like sports, music, and business. Okay. Now there are going to be 100 words in each document. So for each word location, I'm going to first figure out what topic it's going to be. Okay, that's ZID. So Z1D will be, let's say, sports. Z2D could be sports again. Z3D could be business. Z4D could be whatever, music, and so on. Okay, the three any of the 3 topics. Okay. Now you've got the topics. Okay. Now beta is you're going to use ZIDs as index to look at this topic distribution. So betas are going to be this 100 length 3. The beta is going to be basically 3 of these 100 length probability mass functions. Why 3? Because I said only have 3 topics. So 3 topics. For each topic, there's going to be 100 length vector. That 100 length vector is a probability mass function. It's just a probability of If it's a sports topic, what's the probability of seeing the word soccer? What's the probability of seeing the word SEC or things like that? Okay. Of course, probability of seeing SEC is lower than probability of seeing soccer. Okay. So it's just these are called topic word distributions. It's just a number of topics, and for each topic, there's going to be a vocabulary length probability mass function. Okay. And so once I've already figured out these random variables, there are topic random variables for each word. Then I figure out what's the word. The word is going to be, if this is a, let's say it says topic sports, then go to beta, beta for the sports guy, get a sample, that's the word over there. Okay. So it's not really a sequence of, it doesn't create a realistic looking article, but it's just a jumbled up thing of like that topic composition, which is 30% sports, 30% business, 40% music or something like that. Okay. So that's the model of how a document looks like, and that's for D documents. And given that, you can learn a lot of things. Okay, you can learn, for example, given a document, you can figure out what is this topic composition if you know the parameters. The parameters are going to be what? Alpha and betas. Okay, given alphas and betas and the document, you can figure out anything about these random variables. What's the topic composition of the document? Or what is the ZID for each word, for example? Things like that. Okay.
What determines the row number of beta? Is it the number of documents or words?
Oh, I said there are three topics, so that's why there are three columns of betas: beta one, beta sport, beta business, beta music, and each row in that beta is a lexicographic ordering of the words in the vocabulary.
Okay.
Okay, like soccer would be at the bottom part, and then SEC would be right next to it. Apple would be somewhere at the top, things like that. Yeah.
So ZID would have n words, and you can have a topic associated.
ZID is like saying which topic. It's going to be ZID is going to only take three values.
What is the topic? The second placeholder.
What's the topic? And there are only three topics. So yeah,
Right.
it's like one of these three.
T1, T2, T1.
Yeah, precisely.
Then WID is where for T1, say in the first
Yeah.
position.
If it's T1, then you go to beta, sample it from.
I bag of words from T1 and I sample and I put that word into this placeholder.
Yeah, from T1. I mean, these are all the same words, except for there will be higher probability of, if it's a T1, then there will be some words which will have higher probability than T2 guys, and so on. Yeah, that's the word that you put. And so ultimately here, the document is just a collection of, it's like a bag of words representation. Okay, it's not really, there's no order relationship. Okay, that's the LDA model, and it's a graphical model in the sense that, I mean, here I've already written it in plate notation because I did not want to expand it the way we saw Naive's graph, but it's just a graphical model. Okay, so here's the thing, right? So because these guys are all graphical models, if I just know how to work with a generic graphical model, how to do inference or learning, then you can just literally apply those algorithms blindfolded for any of these settings. Okay, and they would work. They may be inefficient, but they would work. Okay, so that's what we are doing. And on the left is a slightly simpler model. Okay, so I will not describe it. You can read it and figure out the difference between this guy and this guy if you want. But let's move forward. Okay, any questions about that? The last example, I'll not spend too much time on it. It's called conditional random field. Okay, again, a model which is actually an example of what is called an undirected graphical model. So, hidden Markov model that we saw before, the naive model, and the LDA, they are directed graphical models. Okay, the edges are going to be directed, and we'll kind of revisit them again when we talk about directed graphs. But conditional random field is an undirected graphical model, and it has this word conditional, which just means that it's gonna relate random variables y's, okay, condition on a bunch of other random variables. Okay, so it's never gonna look at the joint distribution between x and y. It's gonna always try to specify the conditional probability of y given x. Okay, and so generally, for example, y's could be parts of speech, and x could be the sentence itself, things like that. Okay, or y's could be entity, whether it's an entity or not, and things like that. And x could be the sentence. Okay, and the conditional random field has this type of a I'm not drawing the graph here because the graph depends on what these functions are. But the conditional probability of y given x has this very messy form. Okay, it looks messy right now, but I will describe what this z function is, what this phi of c function is when we talk about undirected graphical models. Okay, these have some specific names. Okay, these are called potentials or factors. This is just a normalizing constant, and this has to look like a conditional probability so that it sums to 1 and all that. So there's nothing magical going on here. All it's saying is that the conditional probability of me seeing some parts of speech given a sentence is proportional to some features of the sentence and the parts of speech. Okay, how likely is this part of speech and this word in that sentence in this location? Things like that. These are just feature extractors. Okay, some feature functions. Um, and z of x has a specific name. It's called a partition function. Some of you might have heard of this function called partition function. It's a very expensive expensive function to compute because there's a summation of all values that y can take. So if parts of speech, then for each location, there's so many parts of speech that can be there for each word, right? So it's like an exponential sum here, and so there's a problem with like computing that denominator. But anyway, so this is the conditional random field. Very superficially, it's just some joint distribution between variables that you care about and variables that are conditioned on as some sort of a factorized form like this way. And we're going to look at this. What is the denominator? What is this each factor here soon? Okay, towards the end of this lecture. So, any questions about these 4 applications? It's just teasers for like there are some supervised learning problems, there's some unsupervised learning problems. They're all like graphs, some sort of graphs. So now we'll kind of abstract away and say, oh, what does a graph kind of encode, and what can I understand about this graph first, and then next lecture we'll talk about computation on these graphs, like inference, and last lecture we'll talk about learning parameters of these graphs, things like that. Okay. So let's start with the primer on graphs. So this is going to be, it's a good time to look at this before we jump onto the directed versions. So how many of you have seen graphs before, like graph theory, or somebody has done a course in graph theory? A couple of people have done a course in graph theory. So for you guys, it's going to be a recap. But for us, we don't really need too much of details. Actually, it's a very good, I guess, not quiz, but an interview question or a internship interview question to kind of write a data structure for a graph. Okay, like a data structure for a graph where you can represent. How do you represent the graph? Okay, in code, as in your program. There are different ways to represent graphs. You can use linked lists or anything like dictionaries and so on. So or you can even use matrices where there's something called adjacency matrix. But anyway, that's a good interview question to look at. But okay, what is a graph? For us, a graph is just going to have 2 components, edges and vertices. Edges are nothing but links, vertices are nothing but nodes, same name. Okay, and the relationship between these 2 guys. Okay, so 2 entities, a bunch of nodes, a bunch of edges, and they're going to be related to each other. And heavily used in CS and programming. And we'll look at, in fact, we've seen graphs before when we've talked about spectral clustering and those types of problems. Okay, I don't know if you remember, there's a similarity matrix, and similarity matrix corresponds to a graph which has a Laplacian, and you take an eigen decomposition of it. So there's something in relation to clustering. Okay, graphs are nothing but graphs encode relationships between nodes, and nodes could be like items, right? Like for example, nodes could be movies, and edges between movies correspond to this movie may be very similar to this other movie, and so on. Okay, so graphs can encode various relationships. Here we'll only look at some terminologies which are useful for us for our joint distribution, and the first terminology is undirected. Okay, that's the keyword, undirected. Undirected just means as simple as it means edges have no direction. So what are the edges? So this is a graph with 5 nodes and 1, 2, 3, 5 edges, and these edges don't have direction. So there is no edge. How do you represent this edge? So the name of this edge is going to be 1, 3 or 3, 1. You can use that either because there is no direction, and there are 5 edges like this. Okay, so you can write down the list of edges and list of nodes for this graph. Okay, and we're going to typically represent vertices using 1 to n, or sometimes people use the letter capital V. The size of the graph is the number of vertices, so which is like the cardinality of V. Okay, cardinality of the vertex set. The edge for an undirected graph is nothing but a edge is represented using this name I comma j, which just literally means there's an edge between I and j. Okay, but I and j is the same as j and I, and it just means that I and j are directly connected, and we saw the picture before. So simple computations like maximum number of edges is n choose 2. Okay, there are n number of vertices. Every node can have a edge or not. So these are all the choices. Okay, so the maximum number of choices that you have is basically order n square or n choose 2 number of edges. Okay, and but every pair of nodes need not have an edge between them. Okay, sometimes, for example, in the previous picture, you don't have an edge between 3 and 4. Okay, but there is a path between 3 and 4 which goes to 1 and then goes to 4. Okay, so 3 and 4 are connected. So this is the keyword. Okay, 3 and 4 are connected if there is a path of edges between them. Okay, and a subgraph of G is basically dropping the a subgraph of G is another graph where you drop a bunch of vertices and edges which are kind of dangling. Okay, and here's an example of a path. A path is nothing but a sequence of vertices. Okay, a sequence. These are all keywords. Okay, a sequence is very different from a set. A sequence has this order relationship, so you can't just jumble up the entries of a sequence. Uh, uh, a sequence of vertices where each successive pair are connected by an edge. Okay, so that's what a path is. A path is nothing but so, for example, 3, 4, 3, 1, 4 is a sequence of vertices where 3 and 1 have an edge between them, and 1 and 4 have an edge between them. Okay. So 3, 4, 5 is not a path, for example. Any questions about this for people who have not seen graphs, or is it too simple? Okay. So for those of you finding it too simple, this is fine. But just remember the terminology that we're going to use. So there's also going to be a notion of a neighbor. Okay. So neighbor is nothing but all vertices that share an edge with a given node. Okay. So the given node is the node we care about, and we care about its neighbor, a given node's neighbor, and a given node's neighbor or neighborhood is going to be all those nodes or vertices that have an edge with this node. Okay. So we'll just use NBHT as a short form, but that just means neighborhood. Okay, neighborhood of a node X. For example, 3, 4, and 2 are neighbors of node 1 because it's connected. These three nodes are connected to 1 by a single edge. Okay, between them. 5 is not a neighbor of 1. Okay? I mean, 5 is maybe a 2-hop neighbor of 1, but yeah. So next is the notion of a clique and an independent set. Okay. So what is a clique? A clique is basically a collection of vertices, okay, that are all directly connected to each other. Okay. So if you have 10 vertices, all those 10 vertices are connected to each other directly. Okay. It's like so which means that if they are all directly connected to each other and there are 10 vertices, then there has to be 10 choose 2 edges. Okay. If you just focus on those 10 vertices. So basically, in other words, if I focus on those 10 vertices, the induced subgraph, okay, induced subgraph just means drop everything else which is not those 10 vertices and all the dangling edges. Then that induced subgraph is supposed to be what is called complete. Okay, complete is a keyword. It literally just means that every node is connected to every other node. Okay, and here is an example of a clique. An edge is an edge is a clique with just 2 vertices. Okay? Because if you only look at 2 vertices, that's connected to every other node in the set, which is the other node by a single edge. Okay? So an edge is a clique. What is an independent set? Independent set is a set of vertices whose induced subgraph is empty in the sense that there are no edges in that subgraph. Okay, so you can here's an example, right? So let's say this is the full graph with the blue nodes. If you take these 2 green boxes, the nodes in these 2 green boxes, they form an independent set. Okay, because the induced subgraph doesn't have any edge in that induced subgraph. Okay, because in the induced subgraph you drop all these other nodes. If you drop all these other nodes, there's not going to be an edge between these 2. Okay, they're going to be empty. There's no edge set. Okay, so that's why it's an independent set. And so there is notions of what maximum clique and maximum independent set. Okay, so maximum clique and maximum independent set are slightly different from maximal clique and maximal independent set. The difference is that maximum, as the name implies, is the largest clique or the largest independent set in the graph. So let's focus on this graph. Okay, this 4-node subgraph. Okay, these 4 nodes form the largest maximum clique in this graph. Okay, because there is no other clique. So there's a clique because every node here So every node in this set of 4 nodes is connected to all other nodes. So this node is connected to these 3 guys. This is connected to these 3 guys. This is connected to these 3 guys, and this is connected to these 3 guys. Okay. So it's a clique, and you can see that it's a complete graph here, complete subgraph. But it's the maximal one because I don't see any other clique which is of size 4 in this graph. Okay. So that's the maximum clique. But there are also maximal cliques. Maximal cliques are just those cliques whose size cannot be increased. Okay. For example, this edge here is a clique because an edge is a clique. Okay, includes two vertices, which is a complete graph as well. But that's not a maximal clique. The maximal clique is going to be these 3 nodes. Okay, because that's part of a bigger clique. Like I can expand and have a bigger clique. Okay, so that's why it's called a maximal clique. Any questions about this part? Cliques and independent sets. For us, independent sets are not very important, but cliques are going to be important in the undirected graphical models case. Okay. Okay, so now let's look at directed acyclic graphs. So actually, so far what we've seen is actually undirected. Okay, we did not talk about direction. Now we're going to look at directed and acyclic graphs. Okay, two words: directed and acyclic. So let's look at what directed means. Directed means, as the name implies, there's going to be a meaning of direction on the edge. Okay, so u comma v means there is an edge from u to the second argument v. Okay, so there's a notion of direction, and the graph may also have an edge from v to u. Okay, that's going to be a different edge. Okay, so there's an order relationship when you describe an edge. Okay, so edge named u comma v is different from an edge named v comma u. Okay, and so that's it. That's a graph with these directed edges is a directed graph, and directed acyclic graph just means that there are no directed cycles. Okay, so what is a cycle? The cycle is again a technical term. It just informally just means that there's no way to follow in this case there's no directed cycle. It just means that there's no way to follow the oriented edges and come back to the original vertex from any vertex. Okay, so you pick any node as a starting node, you keep following some directions, hopefully the best directions that can get you back, but there is no way to get you back by following those directed edges. Okay, here's an example. There is no way to start from any node and get back to it. Okay, for example, let's say you start from 4, you go here, you go to 2, but this is not a directed edge. Okay, this is not in the direction with which you can go. Okay, so that's why it's a directed acyclic graph. Any questions here? So this is a DAG, and so let me say in DAGs, there's going to be a slight nuance. We're going to use directed paths when we talk about using direction information. When we talk about paths, whether it's directed or undirected graphs, it's all about ignoring the direction. Okay, so when I just say path, it's always ignore the direction. When I say directed path, now you consider direction. Okay, especially in a directed graph. Okay, so path is, for example, even though there is directions here, a path is, for example, 3, 1, 2 is a path. Although the direction of the edge is actually from 1 to 3. Okay, there is a path here. Okay, a directed path doesn't exist from 3, 1, 2. A directed path would be something like 4, 1, 3. Okay, so that's a directed path. And next, for directed nodes only, so for directed acyclic graphs only, or directed graphs in general, there's this notion of parents of a node. Okay, this is like a specialized topic like neighborhood. Neighborhood of a node is what we saw 3 slides ago. This is specialized to parents of a node. Okay, so given a node, it's just all those vertices which have directed edges to this node. Okay, so in this graph, the parents of C are A and B because A and B nodes have a directed edge to C. Okay, that's why those two are parents of C. Okay, and for example, in this below graph, A is the parents of A. There are no parents of A. Okay, it's the empty set. And the graph on the right, parent of X4 is X3. Okay, very simple examples. Is there any confusion with this? Okay. And now next is the notion of just like parents, there's a notion of descendants, but descendants need not be one hop descendants. Okay, so parents have to be one hop away from you, but descendants need not be. Descendants just mean I'm not talking about children, but descendants. So you can imagine, as the name implies, it could be grandchildren and all that. So all nodes that can be reached by following the arrow directions from this current node. Okay. So for example, the descendants of A in this graph are going to be C and D, but not B. Okay. And similarly, in the right graph, the descendant of x3 is going to be x4 because that's the only node you can reach from x3. Okay. So last couple of notions. So first is the notion of a connected graph. Connected graph is a graph where there's a path between every two or any two vertices. Okay, so you pick any two vertices, there has to be a path between those two vertices. Okay, so you just need a path. So if it's a directed graph, we don't care about directions, but we just need paths. Okay, so ignore the directions, and at least if you can identify paths, then it's a connected graph. If the graph is not connected, if we can't find paths between every pair of nodes or every pair of vertices, then what we have are called connected components. Okay, so it's like pieces of a graph where it's like islands which are not interacting with each other. Like really, like in the ideal case, these are like clusters. Okay, there's no edges between across the clusters, but there's only edges inside the clusters. Uh, so basically, these are just connected components are just subgraphs determined by mutual connectivity. That there is at least a path among all the nodes in that subgraph. Okay. So here's a very simple example. Here's a connected graph because everything is connected. There's a path between every pair of nodes, and here's a graph with two components. Okay, two connected components. This connected component and this connected component. Okay. And the last concept is about what is a tree and what's not a tree. A tree is basically if for any pair of vertices, there's only one path between those two pair of vertices. Okay, so there should not be more than one path between any pair of vertices. So for example, if I look at C and E, first of all, this is connected, right? There is no every pair of nodes. There is there's some way to get from there to there. For example, C and E, there's only one way to get from C to E. Okay, that's the characteristic of a tree. A tree is nothing but any graph where the only way to get from a node to another node is to follow a single unique path. There's not going to be two paths. And here is an example of what is not a tree. Okay, because this is not a tree because there's multiple paths from C to E. Okay, so you can go up and then this way, or you can go down and get to E. Okay, so there are two paths to go from C to E. Okay, so one is called, I think you can use these words if you want, singly connected and multiply connected. This graph is also called a loopy graph or a general graph. This graph is called a tree. Okay. So any questions up to this point? Okay. So now let's start some discussion about directed graphical models. Okay. So now so we already saw 4 examples. Okay. 3 of them were related to directed graphs, LDA, Naive model, and hidden Markov model. But now we're going to abstractly talk about these graphs. Okay. And because we want to understand why do we need graphs. So far we've said, oh, this is a graph picture, there's a joint distribution, and you can do some learning or whatever inference. But why do we need graphs? And the whole point is we need those graphs because we want to encode conditional independence or this domain knowledge. Okay, and we'll see that. So I'm going to use the acronym DPGM. It just means directed probabilistic graphical model, and it's also called a Bayesian network, as I was mentioning, or a Bayes net. There's nothing Bayesian here yet. Okay, in the sense of there's nothing Bayesian in the sense that although there's a name Bayesian network, there's nothing Bayesian in the sense that we're not really working with posterior distributions and priors and some Bayes rule and all that. Okay, we are not doing that yet. There's of course the notion of a joint distribution, so that is there. And what do these graphs ultimately have to encode? Some information, and that information is only conditional independence information. Okay, and this information is going to be relevant to us in our supervised learning and unsupervised learning problems. So let's. So the question is, okay, why do I care about this domain knowledge, right? In particular, why do I care about conditional independence information? Is that that conditional independence information can really help us in doing very fast inference. Okay, for example, just as a teaser, some of you have done 575 with me. You've seen Gibbs sampling, right? So you've seen Gibbs sampling where you'll have variables u1 to let's say up, and to get a sample from this distribution over u, you'll kind of use u1 given u2 to up, probability of ui given u1 to ui minus 1, ui plus 1 to up, right? Generally, these types of conditional probabilities are what you need. If you can sample from these guys, you can get samples from this distribution in a Markov chain fashion. And we'll revisit this idea, okay, in some detail next lecture. Now, these conditional probabilities, if things are conditionally independent, you can drop some variables, okay? Because let's say condition on U2, U1 has nothing to do with all these previous guys, then you can just drop them. You can just sample from U1 given U2. Okay, so then that means it's faster. Okay, so it's a faster inference technique. Of course, here the inference is to sampling, but I'm just telling you that conditional independence can really speed up a lot of inference steps. Okay, computing marginals, computing conditional probabilities, or even sampling. Okay, so let's start with the base object. We always we're thinking of a joint distribution, but we want to attach a graph. In this case, a directed graph. So let's say our base, let's say we have three random variables. We'll start simple for the first few minutes. We'll only think of three-dimensional random variables, three random variables. So the joint distribution between A, B, and C. Okay, so it's gonna, if I don't tell you anything, okay, at this point, there's a joint distribution between A, B, and C. I can just factorize it in any way. So here's one example factorization. I say, oh, there are three random variables. I can say probability of A, B, and C is equal to probability of C given AB times probability of AB. Okay, why is this true? This is just a definition of conditional probability. Okay, you can just apply this, right? This guy is this joint divided by this denominator, right? Similarly, now I can say, oh, probability of AB, I can again apply conditional probability definition. Probability of AB is probability of B given A times probability of A. Or I could do the other way, probability of A given B times probability of B. Anyway, so this is one factorization of this joint distribution. Okay, for that I did not need any information. I could have factorized this joint distribution in any three-term way. Any way I could have started with B given AC times C given A times probability of A, so on. Okay, we can always do any factorization like this factorization. And but given a factorization, we can attempt to create a graph. Okay, so here's a graph. If the factorization is like this, probability of C given AB times probability of B given A times probability of A, then what we're going to do is create three nodes, because first of all there are three random variables. So we'll create three nodes, A, B, and C, and each of these we can think of them as a factor. Okay, in the product, in the factorization, and we were going to create some directed edges. Okay, so we created a node for C, node for B, node for A, and because C depends on A and B, I'm going to create two incoming edges into C from A and B. Okay, so this is like an incoming edge. It's just a plot from matplotlib, I think, or yeah, or Network Explorer or something. So there's an incoming edge from A, incoming edge from B, because there's a factor C given A comma B. And now there's also a factor B given A, so there's an incoming edge from A to B. And P of A, there's no incoming edge to A. Okay, so that's an example graph that I drew. Okay. As you can see, I created directed edges. So these are the three directed edges. And as you can see, there's no directed cycles. Okay, this is a directed acyclic graph. Okay, there's no directed cycle here. Okay, it's a DAG. Okay, but there is nothing special about this factorization, right? I just arbitrarily decompose the joint distribution into three factors like this, and I just drew a graph. We could have factored into a completely different way. So first of all, what I'm trying to say in this slide is that factorizations are not unique, so these graphs are also not unique. Okay, if I don't tell you any additional information. Okay. Yeah.
So conditional dependency does express the directionality.
Conditional dependency.
Yeah, it does express the directionality. As in C depends on A and B. So
yeah, if you know the generative process of how these random variables are related to each other, then you can draw a graph with direction, which kind of shows that first you need to generate the parents and then you generate the children of the parents. Okay, so we'll talk about the directionality soon. Okay. So right now we just had a joint distribution A, B, and C. Nothing else was given. We just factorize it arbitrarily like this. Given this arbitrary factorization, this is the candidate graph. That's all we did. Okay. Uh, so now I'm gonna introduce some information. Okay, that's the conditional independence information. So that's one additional. This is what is an example metadata information. Okay, if C is conditionally independent of B given A, if I tell you this, okay, I just know there's a joint distribution between A, B, and C, but I also tell you that C is conditionally independent of B given A. So, and by the way, this fact is generally written in short form as C perp B given A. Okay, that's a perpendicular sign. It just means that probability of C given AB is probability of C given A. Okay, so that's what. So if C is conditionally independent of B, then B taking a value has nothing to do with C taking any value. Okay, so you can drop this B. That's what's happened here. And if this is true, then we get a different graph. Okay, where C incoming edge from C is only from A, and there was no. So we dropped an edge from B to C. Okay, so if we knew this metadata, then there's a different graph. Okay. Um, and and the important point is that not every distribution could have led to this graph, in the sense that because it told you this metadata, this led to this graph. Okay. Not every joint distribution between A, B, and C can lead to this graph. Okay. So that's first non-trivial property. So let me not go into that. So is this clear? So previously, any arbitrary factorization, you can draw any graph like this. In fact, it's going to be like uh, some DAG, okay, where it just follows the factorization principle. I mean, the terms of the factorization. But here there is no additional information, no conditional independence information. So that's why I got this graph. Now I added a conditional independence information, given that this is a graph where I've dropped an edge between C and B. Okay. So that's the delta. That's the difference. Yes.
How did you determine that it would equal P of C given A? Like, wasn't the information possibly sufficient to remove both A and C, A and B?
So we only said C is conditionally independent of B given A. So given A's value, C has nothing to do with B value. That is encoded like this. So if you look at the joint distribution factorization, we have this distribution, right? P of A, B, and C is P of C given AB times probability of B given A times probability of A, right? In that, we are just dropping this to P of C given B, okay, times probability of B given A. Wait, sorry, this given A. So we are dropping a B here because that's what we can drop B here. So C given A, B given A, and P of A. Okay. So that's not a factorization. That's not something that you would have gotten without me telling you. If I did not tell you this information, you cannot get this. Okay. You would only get this factorization. But then any such factorization you would get. But now you've got a different factorization. So because this is the factorization, there's a graph which is different from that full graph that we had. Okay. So what I'm trying to say is that maybe looking at this graph, you can probably write this factorization because you can see, oh, C depends on its parents. Okay. C given its parents is A. C given its parents. B given its parents. P given A. And there's going to be term for A itself. So P of A. Okay. So looking at this graph, I can write this down. Okay. At least this much down. Okay. There could be more properties like C may be independent of A itself, so this may not be. You can drop A further, but that information is not there in the current graph. Okay? So that comes to my next point. But right now, what has changed from previous slide to next slide? I just added one additional piece of information. So now I have a graph which encodes the conditional independence property. Okay. Any questions up to this point? So all we went was from like a complete graph, like not complete graph, but like a whatever the clique to a graph which only has which has one edge removed. Okay. Now I want to say that that's from like having that full factorization, graph corresponding to full factorization. I dropped an edge, but now I want to say that given the graph, I cannot tell you. There could be many factorizations which agree with that graph. Okay, in the sense that if I show you this graph, you can of course write this. Okay. From this graph, you can see that C only has a parent A, B only has parent A, and A doesn't have any parents, so you can write this. But the factorization of A, the relationship between A, B, and C is at least this much. It could be even further. In the sense, C could be independent of A, B could be independent of A. But then this graph is not capturing that information yet. Okay. So there could be further information which is not captured in the graph, but the graph is at least capturing that information. Okay. So if the joint distribution A, B, and C was just P of C times P of B times P of A, this would still be a valid graph. That's what I'm trying to say. Because if you don't know that information, how would you draw the graph better? If I only tell you this, then you will only draw that. Okay. So for that, I mean, there's a little bit of a formal way to say it, that there's a distribution P, a joint distribution between the random variables or the random variable itself, respects a graph. Okay, respects a graph. So there's a joint distribution, there's a graph. Okay, the joint distribution respects a graph if the joint distribution factorizes. Okay, factorizes according to the graph. Okay, so P of xi given parents of xi, and in the graph you have xi with incoming edges from parents of xi. So if those two match, then that distribution agrees with or respects that graph G. Okay. So that's the definition. Um, Here, this factorization respects this graph. Okay. Without this edge, because C given parents of C, B given parents of A given parents of A, but parents of A are not there. C and B's parent is A, so that's what this graph is representing, right? Remember, in the graph, I can read parents, right? I can in a directed graph, I can literally say, oh, if there's a node, there's a parents of that node. Those are exactly the factors here. C given parents of C, B given parents of A, sorry, B given parents of B, and A given parents of A. Parents of A are nothing, so yeah. But so from this point onwards, I'm making a different statement. Okay, the statement is that the graph does not imply that the random variables are conditionally dependent. Okay, so now we are talking about a slightly different point, which is trying to say that, oh, if I show you this graph, okay, if I show you this graph, doesn't mean that C is actually dependent on A. Okay? So the graph is not encoding a dependence relationship. Graph is definitely trying to capture the conditional independence relationship, but the graph cannot really say whether C is independent of A, for example. Okay? C given parents of A, the graph will capture that, okay, there is a term called C given A, but that doesn't mean that those two random variables are conditionally dependent. Okay? That's all I want to make a point for. So let me give an example actually. Okay, what is the point here is that the graph does not uniquely determine the probability distribution P. Okay? So in the previous slide, we went from full factorization, regular factorization without any additional information. One conditional independence information led to a graph, but there could be other distributions which also could lead to the same graph. Other distributions which also respect that graph. Okay. So what are those distributions? Let's see by example. So let's say A, B, C are independent. Okay, so P of A, B, C is just P of A times P of B times P of C. Okay, then this is a graph where there is no edge between anything. Okay, this distribution respects this graph. Okay, so this joint distribution between A, B, and C respects this graph because literally the parents of A is nothing, parents of B is nothing, parents of C is nothing. Okay, so this joint distribution respects this graph. But this joint distribution also respects another graph, okay? This another graph G prime, because this graph has parents. C has parents. Okay, C has parent A and B. A doesn't have parents. B doesn't have parents. Okay. So, from looking at this graph, I can say, oh, maybe the joint distribution is P of C given AB times P of A times P of B. Okay. But there's additional information here that P of C given AB is just P of C. Okay. But that's more information on the distribution side. But the graph is just capturing. So what I'm trying to say is that these edges, presence of these edges doesn't mean that there is dependence. That's all I want to make a point. Absence of an edge means that there could be independence, conditional independence or independence. But presence of an edge doesn't mean that they are actually related in the distribution. Yeah.
So just because you have A to C doesn't mean C depends on A. That's
Yeah. In the graph, if you make an edge from something to something, doesn't mean that it's actually related.
So just because it has a parent doesn't mean there's actually a relationship.
Yeah.
So would you say the absence of an edge is more informative?
Yes. Absence of edge is the only thing that the graph is trying to encode. Okay. So when we look at graphs, we only care about absence of edges. Presence of edges may or may not be, maybe there's dependence, maybe there's not be dependence. Good point.
Probably A and B are like independent over here. There's absence of like that.
Oh, there's no edge between A and B. There's no edge between A and B. But we'll read these conditional impedance properly. Okay, let me not do an on-the-fly computation for this graph. I mean this slide is literally saying the same thing. What I just said. The G prime is not saying that C depends on A and B. It only says that this ABC factorizes in that particular way. So C given AB times probability of B times probability of A. That's all it says. So it's just that factorization is true. Okay. So this factorization is true. Of course, this factorization is true is because this guy is also actually equal to P of C. Okay. So there is no flaw with this factorization. So it's just the presence of edges don't mean much, but the absence of edges capture something. Okay. Similarly, that same factorization, P of A times P of B times P of C also reflects this graph. Okay. Because this graph is like the full factorization graph where you're not really capturing anything. Okay.
How would we actually draw a graph when A and B depends on, or C depends on A and B?
Yeah, so C is depending on A and B. Okay, if C is depending on A and B.
Actually depends on.
Yeah, so here, if I draw this graph, it's not clear. So for this graph, we already know, P of A, B, and C. Sorry, A, B, and C is P of A times P of B times P of C respects this graph. Okay, this thing respects this graph, but we also know that if I only look at this graph, I don't know. So I can only say this, right, is equal to P of C given A comma B times probability of B given A times probability of A. So by just looking at this graph, I can only say this. But this is equal to this, is the additional information that is not being captured in this graph. Okay. So the graph is not capturing more information here. Okay, but in terms of distribution, it is true. Okay, this distribution respects this distribution, independence distribution respects this graph. Okay, but there are better graphs to represent this information. So that's all I mean. So for a given distribution, there could be multiple graphs that kind of are faithful to it, but some graphs have more information than others. Okay, so by just looking at the graph with this edge connection doesn't mean that there is dependence between these edges. Okay.
So what's the use of making an edge?
Absence of an edge is what is important. Okay, having if you don't know anything, you can just put edges between everything. Yeah. So if you don't know anything, but now I'm giving you metadata, which is this domain independence. You're dropping edges. Now there's information. Okay. So if I drop an edge, for example, if I drop an edge like this, then this is not true. Okay. This is not a distribution that is captured over there. Okay.
So I should start with a clique and then keep dropping edges as a
Yeah, that will be like not exactly clique, but any full factorization graph. And if you drop edges, now you're adding more and more information. Yes. So here's an example. It's not very useful at this point, but it's basically what is called, basically a Bayes inversion of regression. Okay, Bayes inversion of linear regression. So what is the Bayes inversion of linear regression? All you're trying to say is that the weights or the beta vector coefficient, okay, the weights, the beta 1, beta 2, beta n, or in this case I'm using capital W, they are random variable. Okay, so regular linear regression, we know, our function is W transpose X, or don't worry about this phi transformation, just think of it as like nonlinear transformation, feature engineering, okay, transform space. My prediction is some beta transpose or W transpose X here. Now W has become a random variable. Okay, so that's Bayes in linear regression. If W has become a random variable, you will have a graph like this. Okay, where W relates to the prediction 1, prediction 2, prediction n. Okay, without knowing W, these are all related to each other. Okay, these random variables are related to each other. Knowing W, these random variables are conditionally independent of each other. Okay, so that's the so looking at this graph, you can say that y1, y1 and y2 are conditionally independent of each other given W. So that's the otherwise you would draw a graph where everything is connected to everything else, like maybe edges between y1 and y2, but that doesn't make any sense, right? In the linear regression problem, y1 has nothing to do with y2. One observation has nothing to do with the other observation. We assume independence. Okay. So here it's not. We are not going to assume independence. We are going to assume conditional independence. Given the value of w, one observation has nothing to do with the other observation. Okay. Um, yeah. So I mean, all it just means is this joint distribution between the parameter, the linear regression parameter, and the outputs is a product like this. It's basically very similar to the Nye-Bayes type of a situation. And we saw this plate notation before. If you had a graph like this, you compress all these into a plate where the n such values of that random variable. Okay, it's just for ease of drawing the graph in this case. And what is latent is W. You never observe W. You only observe X's and Y's. Okay, so Y's are observed, W is never observed, and so there's some names. Okay, well, W is called latent variable, and Y's are called observed variables. And we have seen this. Latent dirichlet allocation. The part which is latent is the topic distribution for each document, and the ZIDs for each document D. Okay, so those are latent. Okay, so yeah.
What was the character feet? And what does that represent in the previous slide?
Phi is just a feature engineering term. You can drop phi. You can think of phi as identity function if you want. Phis are just like you have the original raw variables, you transform it into a new set of variables which are like transformed variables, and then your output is linear with respect to that transformed variable space, like square root, log, x1, x2, for example, product like that, things like that. Uh, yeah, so let's actually take a break now and resume at what's the time? Okay, 8:05. 8:05.